All right, so now that we've kind of talked about the basics of SIMS, we've talked about a lot of the instrumentation involved in SIMS, let's look at the actual spectra. So what we get as results. All right, so in SIMS, we talk about ions. Well, we can yield either positive ions or negative ions. So that's kind of something different that we see because we can get either positive or negative charge. But we typically need to do them separately. And so the positive ion spectra for something like polystyrene can be seen here on the left. So again, you have the M over Z ratio as the x-axis, and then we have count. So how many of those ions that we see. And then we have the negative ion spectrum for that same material on the right, but same plotting of it. We look at a certain M over Z ratio, and we have specific counts. And so basically, we have one material could have a number of different peaks based on the different fragments of that material. So as you see here, polystyrene is very complex because we have different fragmentations of that structure that give us different mass ratios. So there's lighter ones, there's heavier ones, and obviously we can have different charges as well. And so typically what we're doing in these cases is matching up a spectra of our material to known spectrum of various materials. So as you can kind of see here, SIMS spectra are more complicated than XPS or AES because here we have to deal with what we call ion fragmentation. So fragments of a material. So let's take the example of sodium nitrate, NaNO3. So when we bombard this material and produce ions, we can produce different fragments of this molecule. So we can have OH groups from that. We could have NO positive, NO2. And so you see that there's different fragments of this spectrum that we could have. And so here over on the actual spectrum, the negative ion spectrum for sodium nitrate, we see those different containing groups. So we can get a hydrogen negative ion. And so if you think about that, we are talking about 2 electrons. And so then we have oxygen, we can have hydroxide, NO minus, NO2 minus. So those are all kind of possible fragmentations of this larger molecule that we have. If you go even higher, you can have the NO3 group, and then you can have different versions at even higher. So there's a lot of different possibilities as opposed to an electron from an copper atom has a specific binding energy, right? And it might shift because of the chemical state, but we only have one value for that. And so it's less complicated for something like XPS or AES compared to SIMS, where we have all these fragmentations. However, identifying elements is relatively simple compared to molecules and polymers. So something like cesium here will have a specific mass and charge, and so that is easy to detect. So if we use time of flight, it has a specific time, and so that's easy to detect. And also, we talked about it early in the advantages of this technique. If there are isotopes of that element, we can also see them as well. And so if we have isotopes of cesium, we could see that with slight shifts in the mass, because that's what defines an isotope. But the advantage is, so even though it's more complex, it does allow us to study the chemical structure of polymeric materials, right? So we can look at different functional groups and different fragmentations. And so when we look at the relatively high regions, we can get different information. So again, this is polystyrene. It has a monomer mass of 104. And so anything less than 104 gives us basic structural information about the monomer. So all of this kind of gives us structural information about the monomer. But also, we know polymers form larger macromolecules. So if we go above 104, we can get informations about what we call the n-mer region. So small numbers of the monomer. And so that's basically what this region is giving us. It's giving us that if we cluster small numbers of monomers together. And so that can be used to study copolymers, how two monomers come together. It can be used to study crosslinking in that material. And so it gives us information on a more macro scale of this polymer. Also, at the highest M over Z regions, so you see here we're up to almost 1,000, up to 1,000 here. And what we see there is the oligomer region. And so this is used in studying the average molecular weight. And so you see here that the peaks that we see are in denominations of 140, which again is the is our kind of repeat structure. And so in this case, it's being used to detect organic molecules attached to silver ions. But we're able to study a much larger structure. And so there's a big range of information that that the SIMS technique can give us.